So we've been talking about energy levels in terms of a ladder. We have these integer values. Where exactly do these energy levels come from? Well, essentially, you can see energy levels on our periodic table. It's each of these rows or periods indicates a new energy level. So as we go down the rows, N increases. So in our first row, our first period of 1, this is our N equals 1 energy level. Within the second period, this is our N equals 2 energy level. And then our third row is N equals 3, and then so forth. Right? So it is really that simple to see the energy levels within our periodic table. It tells you what energy levels are there. So, the periodic table really is a wealth of information, and it's really due to how modern chemists put together this periodic table. We put together this periodic table through periodic law. So remember from, I think, 2 chapters back, we talked about periodic law, where we arrange the periodic table in increasing atomic number or number of protons of the elements. And then when we arrange the elements in a certain way on the periodic table, that essentially similar properties start to arise from the different families, that all of the elements, in group 5 have similar properties to one another. So that's why we see these periodic properties start to pop up, and that's why we call it periodic table, because properties happen or they repeat themselves periodically. So let's keep that in mind with periodic law. We've arranged our elements in terms of their number of protons. Well, now how are electrons arranged in the atom? How can we use the periodic table to our advantage to locate where an electron is? Because we've been talking about this ladder analogy and how in the lowest energy level, electrons are closest to the nucleus, and electrons in higher energy levels are further away from the nucleus. Well, how can I actually determine where exactly an electron is? And so in order to locate one electron, depending on where it is it in N equals 1? Is it in N equals 2? Is it in N equals 3? Well, we actually use 4 what we call quantum numbers in order to locate an electron. So this diagram that you see here on the right, this is just an orbital diagram, which you will be learning how to make, but every single shell that you see here is an energy level. So this first ring around the nucleus, which this particular nucleus has 17 protons and 18 neutrons. The first ring of electrons is our N equals 1 energy level. The next ring is N equals 2, and then N equals 3. So we're still using the ladder analogy, but we're just putting them in circular rings now instead of just a ladder. So anyway, we will be using 4 different quantum numbers to be able to locate where an electron is on our ring ladder system. That will help us locate an electron. So those 4 quantum numbers that I'm talking about right now, those have names. And so we have a shell quantum number, a subshell, an orbital, and a spin. So I will get into the details about the first quantum number, the shell. So this is essentially our energy level, N. This is our energy level. So our shell, or N, is just the region of space around the nucleus that contains electrons. Each shell can hold a certain number of electrons. These N values are the same as our period rows. So what I showed in that periodic table previously, each period row is a shell. So all of the electrons contained here within N equals 1, there are electrons in that energy level, and then in N equals 2, there's this many, we can hold this many electrons. N equals 3, we can hold that many electrons, and, etc. So that is our shell. So electrons in the same shell have about the same energy because they're within the same energy level, and they will spend most of their time at this distance from the nucleus. So remember also, when we talk about energy levels, N equals 1 is closest to the nucleus, while 7 or higher numbers are further from the nucleus. So that's how I, you know, dictated the rings around this orbital diagram, that the ring that is closest to the nucleus is n equals 1, while the ring furthest away from the nucleus is 1, 2, n equals 3. So you go up in integers going away from the nucleus. So the shell, or n value, is our first quantum number. That will tell us which ring that electron can reside in. So if I tell you, okay, I have an electron in n equals 2, then you would know that that electron would exist somewhere in this second ring. Versus if I said, okay, you have an electron in n equals 1, then you know that that electron resides somewhere in here, in that first ring closest to the nucleus. Okay, so with shells, remember shells is our n value. So a little bit more information about shells. Energy of the electrons increase as we move away from the nucleus. So, think of our ladder analogy. As we go up the ladder, increase our energy level, we increase energy. So same thing with our rings. The further away you are from the nucleus, and as n increases, the energy of that electron within that shell increases. So yeah, as n increases, energy of the electron increases, and also a consequence when n increases, that you can have more electrons present in that shell. Because you can see as we go up in n value, our circles are getting bigger, our rings or orbits are getting larger. So if there's more ring space, you can put more electrons in those rings. While closest to the nucleus, this is a pretty small ring. It would be quite hard to pack a bunch of electrons in this first ring. So that's a consequence of, as our n value increases, you can pack in more electrons in that larger n value shell. And so the equation, we can calculate how many possible electrons you can have in a shell. And it's based upon the n value. So the number of electrons you can put into a single shell is equal to 2 times that n energy level squared. So in our n equals 1 shell, right, 1 squared times 2 is equal to 2. So that means in our n equals 1, we can only have 2 electrons. Then in our n equals 2, 2 squared is 4, 4 times 2 is 8. So we can pack 8 electrons in the n equals 2 shell. And then, we can skip over to n equals 5. 5 squared is 25, times 2 is 50. So in the n equals 5, we could pack 50 electrons. So, we can also do like it for n equals 6. 6 squared times 2, that's 36 times 2. We can pack 72 electrons in an n equals 6 shell. All right, so that was shell, our first quantum number. It told us which orbit or which ring the electrons will reside in. Our next quantum number is subshell. And so the subshell tells us the region of space within a shell or within an n value that has electrons of the same energy. So subshells have letter designations. So this is different than our shells. Shells have integer number designations. Subshells can have letters S, P, D, F, and so forth. I think then it just uses the alphabet, F, G, etc. But we will only focus on S and P for the most part. So all of these subshells may exist in a certain ring or certain energy level shell. So the number of subshells that you can have is equal to the n value associated with that ring, because there's always subshells within a shell. So again, subshells can have letter designations. Always start with S. So always think it's, goes S, P, D, F, G, etc. So within our n equals 1 shell, we can only have one subshell. And so you'll start at the leftmost letter designation. So we can only have an S subshell within an n equals 1. So if we were in our second ring around the nucleus, n equals 2 shell, we can have 2 possible subshells. So that means that you can have S and or P subshells within our n equals 2 shell. And I have these two bolded because these are really the only ones I'll ever test you on. N equals 3, uh, our third shell can only have 3 subshells. So again, think left to right with these letter designations. So S, P, and D are our only possible subshells. And then N equals 4 can have 4 subshells, S, P, D, and F. So how do these letter designations, these subshells or sublevels, differ? So sometimes we call them sublevels. Essentially, we mean subshells. So how do those letters differ from one another? So within a certain energy level or a certain shell of N, the S sublevel or subshell always has the lowest energy. So let's remind ourselves. It goes S, P, D, F, and G, so on. So that S, our leftmost letter designation subshell, is our lowest energy. And then followed by P, D, and F in terms of energy within the same subshell. So I can only be talking about, like N equals 2. But remember, in N equals 2, you can only have S and P subshells. But within N equals 2, we know that the S subshell in N equals 2 will have a lower energy than N equals a P subshell. So maybe I can write that. So for example, a 2S, so 2 meaning N equals 2 with a subshell of an S, would have lower energy in terms of the 2P, or an N equals 2 with a P subshell. So yeah, so S subshell followed by PDF in terms of energy. So energy increases. But you still have to keep in mind what are the possible subshells for that specific energy level or main shell, or N number. So lastly, theoretically, higher subshells are possible, right? If I had an N equals 8, then there are 8 possible subshells. So you would have to count out 8, a total of 8 letters to get there. They are possible, but really S, P, D, and F are the only sublevels that chemists need to worry about, because the S, P, D, and F sublevels can describe all of the electrons within all of the elements known to man right now. All right. And then lastly, as N increases, the volume of the subshell also increases. So kind of what we mean by that is, like, if I compared a 2S subshell or sublevel to a 3S subshell, that the 3S subshell would have more energy and would be larger. Okay. Larger in volume. All right. So that takes care of 2 of our quantum numbers, shell and subshell, where shell is our integer numbers, our energy levels, and then subshells are our S, P, D, F designations. So our next quantum number is orbital. And so an orbital is the region of space within a subshell where we are most likely to find a electron. So the number of orbitals in each subshell differs, and it uses this odd counting number. So within the S subshell, there's only one possible S orbital. And so what I mean, so we're talking about orbitals now. This is our third quantum number. And then within the P subshell, there are possible of 3 P orbitals. Within the D subshell, there are possible of 5 different orbitals. And then with our F subshell, there is a possibility of 7 different F orbitals within that subshell. Essentially, what all of these different orbitals are essentially just different orientations of the orbital, but we don't have to focus on that. So just know within these subshells that there are different numbers of orbitals pockets that you could have an electron reside within that subshell, and then that subshell lies within a certain energy level or overall shell. And so what do I mean by orientation? This kind of has to do with the shape of the different subshells and orbitals that we have. So our s orbital shape is just round. It's just this sphere. All right, so you can see here that I have a 1s, this is a 2s, and then we have the 3s. So you can see in terms of volume or size that our 1s is the smallest, while 2s is larger, 3s is the largest. So again, what I mean by 1s is this is an n equals 1 energy level or shell with an s subshell. A 2s is an n equals 2 electron in an s subshell, right? And then 3s would be n equals 3, but an s subshell, etc. We talked about this before. When our n number increases, the size or volume increases. So volume increases. So you can see that here. That our volume increases as we increase our n value for each of these s orbitals. And then if you remember from our orbital quantum number, this is our third quantum number, right? That within an s subshell, we only have one type of 1s orbital. This is because this is a sphere. That the orientation of a sphere doesn't matter. It'll always look the same no matter how you rotate it. So that's why there's only ever one orbital to describe an s subshell. So that might be confusing, but I think if I show you the p orbitals, that might make more sense. So within the p orbitals, our p subshell, right, there's a possibility of 3 orbitals, 3 subshell, p subshell, 3 possible orientations. This is our 3 possible p orbitals, 3 orbitals that are p. All right, so our p subshell, that's our second quantum number. And then our orbital, that's our third quantum number. And I kind of said before that orbitals kind of just tell you orientations. We didn't need an orientation for our s orbital because it's spherical, but within our p orbital shape, you see how it's like this figure 8 type of shape. So if you think of 3D space, I could have this, figure 8 along our x-axis, I could have it along our y-axis, or I could have it along our z-axis. These are 3 distinct orientations, but it's the same shape. And so these 3 orientations are what we mean by 3 possible orbitals within the p subshell. And again, I will only ever ask you to know our s orbital shape and our p orbital shape. If you want to know, the d orbital shape looks kind of funny. It's like 2 figure 8s kind of put together like that. All right, and then our f orbital shape is even more complex. It has even more lobes than our 2 lobes on our p orbital, 4 on our d orbital. But again, you only have to know s and p. Okay. All right, so kind of to put everything together when thinking about sublevels or subshells and orbitals within a certain n value. So remember, each sublevel consists of a specific number of orbitals. If you have a s sublevel, it will contain only one s orbital. If you have a p sublevel, it can contain 3 p's, d 5s, f could have 7. So if we have an energy level of 2, there's only 2 possible sublevels or subshells, and that would be s and p. So we only have to think about s orbitals and p orbitals in our energy level of 2. So, I mean, I could do this for our n equals 3. Can I do n equals 3? So if I had n equals 3, our possible sublevels would be our 3s sublevel or subshell, 3p subshell, and our 3d subshell, because now I have n equals 3, so now I have a possible d sublevel or subshell. And within those subshells, we have specific orbitals. So still, we only have one s orbital. There are, I'll say, one 3s orbital. We can have a possibility of three 3p orbitals. And within our 3D, there are 5 possible 3D orbitals. All right, and so you can do this for n equals 4, n equals 5 as well. Okay, so those are 3 of the quantum numbers. We did shell, subshell, and orbital. So the last quantum number, our 4th quantum number, is spin. All right, so each orbital that we talked about up here, our singular 2s orbital and our 3 different 2p orbitals, or if we had access to our 3D orbitals, there would be 5 of them. Each orbital can hold a maximum of 2 electrons. So this 4th quantum number is spin. Since electrons are negatively charged, we need to overcome that, negative repulsion of the negatively charged electrons. So how we overcome that repulsion is through spin. So if one electron is spinning in one way and the other electron is spinning in the other way, that we can reduce the amount of repulsion that those electrons are feeling when they reside in the same orbital. So that's where our 4th quantum number comes into play, our electron spin, where we can have something spin up or spin down. And that's what is being kind of shown in this diagram right here, where this box is an orbital. So let's just say it's like our 3s orbital or something. So it could be like our 3s orbital. We could have a spin up or a spin down electron in there. If I wanted to talk about the orbitals within like our 3p subshell, so remember there's 3 orbitals within a p subshell, so I'm going to draw 3 boxes. So these are 3 orbitals. So 3p orbitals. So how I would draw these electrons, you would spin them all. So if I had 3 electrons, I would spin them all in its own orbital first, because they're separated, so they won't feel as much repulsion. And then as I put my 4th electron, I would spin it down, the next one down, and the next one down until the whole 3p subshell is filled. Okay, so quantum numbers is essentially telling us the location of an electron with 4 different quantum numbers. So it's like giving an address for an electron. So like our shell kind of tells you like what town you're in if you were an electron. So like I could say, we're at OSU Lima. That's our shell. Our subshell is making it more specific. It might tell you, okay, this is what building you are in your town. So, we might be in our recitation room 170 science building. We're getting more specific. We're telling you what subshell you're in. And then maybe we can be even more specific and try to locate where you, an electron, are on a certain day. So an orbital, our 3rd quantum number, makes it even more specific, where we could say, okay, you're in our classroom on Thursday, our recitation day, right? And then we can be even more specific by saying what time you're in that room to locate you. And that would be like our last quantum number, the spin, essentially telling you in which box you're in which orbital. So again, quantum numbers, it's like just giving an electron location. So we can put together all 4 of our quantum numbers and how we describe them in terms of energy into a comprehensive diagram for all of the different sublevels and orbitals. So right here you see all of it. I don't expect you to memorize this or anything. I just want you to kind of look at it and make sure you're understanding how energy of these different orbitals and sublevels differ as we increase our n value or our shell. So if we start at the bottom, this is, our lowest energy. It's closest to the nucleus, The only subshell we can have within an n equals 1 is our 1s subshell with only 1 orbital. And then within that n equals 1, 1s orbital, we could have either a spin up or a spin down electron, either of those. And so that's what's utilizing all of our different quantum numbers. And then if we go up, we can see we have our 2, or our n equals 2. I don't want to include that one, so just here. This is our n equals 2 shell, where we can have a possibility of 2 different subshells, so our s and p. And within the s and p, we can have either 1 orbital within our 2s or 3 orbitals within our 3p. So those are the 3 quantum numbers, and then the 4th one would be a spin up or spin down, depending on how you fill it, which we'll learn about, I think, in the coming slides, how those electrons are arranged. Right, and then you can keep going up the ladder. Some things change and get kind of different once we introduce our d orbitals. So that's why I kind of just want us to look past the d orbitals and just concentrate on our p orbitals right here, because they follow our trend very, very well. Our n equals 1 and our n equals 2 shells, and our s and p subshells. And then I guess, energy increases, we're further from nucleus. Okay, so like I said, electrons, our 4th quantum number, electron spin, can also kind of tell us where these electrons are residing within these orbitals. So now let's think about how electrons arrange themselves in these different orbitals. That's where we get to here. And how is electron arrangement related to our periodic table and periodic law? So essentially, how atoms and elements arrange their electrons is the reason why we see periodic law. And I'm kind of going to repeat myself in the next couple of slides, but this is really important. It's the electron arrangement is why we see the periodic properties pop up on the periodic table. It's the reason why we have groups with similar properties. It's why groups have similar properties and react the same way. And the reason is because of how electrons are arranged. Elements that are within the same group, so if you look at group 5a, nitrogen and phosphorus, those 2 elements are in the same group and have similar configurations of electrons. So this is kind of where electrons come into play. Protons defined what element it is, but it's electrons that define reactivity and properties. Chemistry really is the study of electrons, and how electrons move around within reactions, how they move between different atoms in chemical compounds. Chemistry really focuses on electrons. And now that we finally introduced electrons and how to describe them, we can really start to get into the nitty-gritty of chemistry. And electrons are super important to us as chemists, but it really was the work of physicists in the early 19th century that kind of brought us to where we are now. So if you remember, in an earlier lecture, we talked about our Bohr model of our atom, where we have our nucleus and our extranuclear region. That was our Bohr model. So we have Niels Bohr to thank for a lot of the work within electrons and how to describe electrons with quantum numbers. And, Niels Bohr, we're kind of taking his approach to physics and chemistry, to describing atoms and their electrons. He really said, what's his quote here? When it comes to atoms, language can only be used as in poetry. The poet, too, is not nearly so concerned with describing facts as with creating images. So that's what we're going to be doing when trying to describe atoms, is create these images that can convey electrons and hopefully give us some insight about reactivity of those different elements. So we're going to be creating images, and this is related to our orbital diagram, which is what you see right here. Diagram. So we're going to be creating images to help us describe facts that will help us understand the atom. Because if I really wanted to teach you about atomic structure the way that I learned in my undergraduate and graduate studies, you would be thoroughly confused. So Erwin Schrödinger is a physicist, and he was the first person to solve the hydrogen atom and really understand the location of electrons within a hydrogen atom. So Schrödinger solved the hydrogen atom problem with a new type of mathematics, a math that's beyond calculus, and that's quantum mechanics. The physics that you learn in your physics class, even in intro physics class in college, that's classical mechanics. So quantum mechanics uses this different type of math that you've, I'm sure, never seen before. So this is Schrödinger's equation for solving the hydrogen atom. So he has a quote right here. The non-physicist finds it hard to believe that really the ordinary laws of physics, which he regards as the prototype of inviolable precision, should be based on statistical tendency of matter to go over into disorder. All right? So if his math is as confusing as his quotes, just going over this slide would take a whole semester for us. So we are going to take the Bohr model approach to understanding atomic structure. That's basically what I want to get at. That these orbital diagrams are fine enough for us to understand reactivity of atoms in this type of classroom. We don't even go over this in 1210. All right, I kind of just show like one slide like this saying like, okay, this is actually how you solve the hydrogen atom, but it's not really useful for our purposes. Essentially, the Schrödinger equation tells us the shapes and locations of electrons, but and it gave us the quantum numbers that we just looked at. The Schrödinger equation solves for those. So maybe I'll just write that. The Schrödinger equation solves for quantum numbers. And that's all you really need to know. But yeah, we're going to take the Bohr approach and try to simplify things as much as possible. I know I keep reminding you that the periodic table is a wealth of information. It really is. Like if I created a list of all the things the periodic table tells you, the list would be like forever long. Now that we're adding a lot of different skills to our toolbox. So here's another kind of depiction of the periodic table, and this helps us kind of apply those quantum numbers that we just learned about. It simplifies it because remember, we're taking the Bohr approach with understanding atomic structure. Remember previously we did talk about energy levels, our N values, our shells. We know that our N value increases as we increase our row numbers or our period numbers. As we go down the periodic table, row 1, where our hydrogen's at, that's N equals 1. Lithium starts N equals 2. Sodium is our N equals 3, and so on. So we know that. We have that covered. What about the other quantum numbers, our subshells? Thankfully, the periodic table, because it's arranged by periodic properties, it tells us our subshells for us. Yay! So our 1A and 2A groups, so, hydrogen and beryllium that's there, this is what we call our S block or S area. So the elements within here have electrons that are within S orbitals. So it's up to you to figure out, okay, what row is it in? But this is an S block. So hydrogen would be, 1S. Lithium going down, that would be 2S. Where 1 and 2, that's our N value. So there's our S block. Our P block is over here, and it starts with boron and carbon. So boron and carbon. Our S block is our 3A elements all the way over to our 8A elements, except helium. Helium really should be over here. Maybe I'll make it purple. So our helium is over here. So that's why that block is purple. That block should be over here, but typically we write helium over here with the other noble gases, so just keep that in mind. But all the other elements within this block, besides helium, are our P block. And so just keep that in mind as we're filling electrons, as you're going through this area. Each element corresponds to adding one additional electron to our count. So there's our P block. And then finally, our transition metals. This is our D block. All right. So there's one electron within the D orbital in this column. There's 2 electrons, 3, 4, 5, 6, 7, all the way out to 10. Okay. And then finally, at the bottom here, this is our F block area. So the periodic table tells you both the subshell and the orbital that electrons reside in. So really it's kind of only up to you to kind of figure out how those electrons become spin paired. And I think I will show that here. So the rules for filling orbitals when we make orbital diagrams. So orbital diagrams, that's what I showed here, what our Bohr fella was showing us, our orbital diagrams. So how do we make one of those? Well, as long as we move across the periodic table and understand where those blocks are, the S, P, D blocks, then we'll be able to do it. So rules for filling orbitals. So first, fill your lowest energy levels first. The electrons will spread out over a subshell before pairing. So remember, subshell means like S, P, whatever, but we're only going to look at S and P. No more than 2 electrons per orbital. So remember, an S orbital, there's only one S, like one singular S orbital. One S orbital. While there are 3 p orbitals within a p subshell. Electrons will have opposite spins when paired, but again, remember step 2, electrons will spread out before pairing in a subshell. And then finally, filled and then half-filled subshells are the most stable configurations, and that will be important kind of at the end here when we talk about valence electrons. But thankfully, with drawing these diagrams, you just have to read it off the periodic table. So if I asked you, for example, draw the orbital diagram for boron. So you would draw your boron nucleus, and then you would start drawing rings. But you want to start at hydrogen. And you know hydrogen, that's a 1s. That's in our 1s block. And then you keep going, you go increase in atomic number until you get to the element you want. So if I said, what is the the orbital diagram for boron? I think that's what we're doing here. Yeah, boron. So let's just do that. So orbital diagram for boron. So first, draw nucleus. So I'm going to draw my nucleus. It's a boron. I'm going to make it bigger. So boron has 5 protons. So just keep that in mind. So there's my nucleus. So I'll draw, okay. So first I'll draw my n equals 1 here. So n equals 1. And then I'm just going to count all of the elements starting at hydrogen in my n equals 1. So my goal is to get to boron, which is element number 5, but I'm going to start at hydrogen. So I know hydrogen, that's a 1s. That's our 1s because it's row or period 1, and it's within the s block. So hydrogen, then helium. So that completely fills my s block. And so you will draw it like this. Since they're both in the s orbital, they'll be drawn right here. So I started at hydrogen, gone to helium. Now I still need to get to 5, so let's go to lithium. So now I'm back into an S block, but now I've increased my shell number, n equals 2, so now I need to draw a new shell. So this is my n equals 2. All right, so lithium and beryllium, that's within our S block. So I'm filling that whole thing. So I will pair those 2 electrons into the same orbital together. Okay, so that's the 2s electrons for lithium and beryllium. And then we get to boron. Boron's within our p block. So our p orbital is different from our s orbital, so I have to draw this electron somewhere else. So I'll just draw it over here. So this is what boron would look like, where there's one or a pair of electrons within our 1s subshell. There are 2 electrons in our 2s subshell, and then there is 1 electron within our 2p subshell. All right, I'm going to just move this so I have room for phosphorus. All right, so there's boron. So let's do phosphorus. Okay, phosphorus is, okay, that's element 15. So remember our tip here, start at hydrogen and go up into increase in atomic number until you get to the element you want. So we need to get to phosphorus, which is 15. So this is going to be a little bit more work, but I know we can do it. So first, draw the nucleus. So phosphorus, that's P. How many electrons? Or sorry, protons. There's 15 protons. I'll just draw it like that. Okay, so there's my nucleus. Great. So I know I will have to start with our n equals 1. That's a bad circle. Okay, n equals 1. So our periodic table tells us everything. You don't have to memorize the orbital diagrams for different elements. The periodic table will tell you it all. So we start at hydrogen, and our goal is to get to element number 15. Just keep in mind the subshell are S and P blocks. So hydrogen and helium, that's our 1s orbital. So I will put 2 electrons in our n equals 1. They're paired together because they're both in the s orbital. All right, so that's the entire n equals 1 row. We're done with n equals 1 because you can only have an s orbital in n equals 1. So I need to draw now is my n equals 2. All right, so n equals 2, we're starting at our second row, or second period, so lithium and beryllium, that's still filled. Okay, so that's our 2s being filled. Move on to boron. So I need to get to 15. So boron, carbon, nitrogen, oxygen, fluorine, neon, that's all going to be filled too with electrons because we need to get to 15. So this is within the p block. So I will also draw these electrons within the p block within n equals 2. First, I will spread them out. So 1, 2, 3. I need to do a total of 6 here within this p block. So I drew 3, and now I'm going to start pairing. 4, 5, 6. All right, so if you've lost track, you know, our inner n equals 1, this was our 1s orbital. Here was our 2s orbital. And then we had 3 2p orbitals. 2p, 2p. All right, but we still don't have enough electrons yet. We need to get to 15, and I've only drawn 10. So our entire n equals 2 is filled now because we can only ever have s and p within an n equals 2. So now I need to draw a new shell. This is our n equals 3. But remember, we're counting the elements. So we stopped off at neon. Now we're going to go to sodium, which is 11. This is our third period. So we're going to start our n equals 3. This is our third period within our s block. So I'm going to draw 2 more electrons because I need to get to 15. Sodium, magnesium, that brings us to 12. That is our 3s orbital. Okay, so I stopped off at magnesium. So now I need to do aluminum, silicon, then phosphorus. So I need to put 3 electrons from my p block. So remember our rule with spreading out electrons within a subshell. So our p subshell will spread out like this. 1 electron for aluminum, another one for silicon, and then finally our last one for phosphorus. So this is what our orbital diagram would look like for phosphorus. So I want to reiterate with this phosphorus example that we spread out those 3p electrons within that subshell. So in this example of phosphorus, there are 3 unpaired electrons. That's super important to know, that you must spread out electrons within a subshell before you start filling up all the orbitals with oppositely spinning electrons. And every time I draw 2 of these paired electrons, know that one is spinning up and the other is spinning down. Let's do another example of drawing the orbital diagram for an element, this time nitrogen. So we're going to go through the same steps as always. We're going to start at hydrogen and work our way up to nitrogen, which is element number 7. So first things first, we're going to draw the nucleus. So nitrogen, it has 7 protons. And we always start with our n equals 1 shell. So n equals 1, we're going to start at hydrogen. We're going to fill hydrogen to helium. So that's 2 electrons in our n equals 1. 2 electrons. All right, so now we're at helium. Helium is 2. To go to 3 is lithium and beryllium. Now we're in our second period. So we're going to add a new n equals 2 row, or n equals 2 shell. those first two electrons in n equals 2 get filled into our s2s orbital. So that's lithium and beryllium get filled. So that brings our electron count up to 4. Now we need to go to boron, carbon, and nitrogen. So we're ending at nitrogen because that's the element it's asking for. So boron, carbon, and nitrogen, those are 3 electrons within the p block. But it's still within the n equals 2 period, so we're going to stay within our n equals 2 shell here. So 3 electrons, we're going to spread them out as we fill them. So 1, 2, 3. So you see that there's 7 electrons for nitrogen, which has 7 protons. Okay, so let's see. How many unpaired electrons are present in nitrogen? So let's see. Each of these, 2s to get 2 electrons together, those are pairs. So these s electrons, the 1s and the 2s are paired. The only unpaired electrons are within our p subshell. So here it looks like there are 3 unpaired electrons. Okay, so let's see how else we can use these orbital diagrams. Okay, so with this other learning check, we're going to give the symbols for the elements that they're describing to us here. So again, it's can we navigate the periodic table and the different the different blocks, like the D block, the S block, the P block, can we navigate that? All right, so this first example, it says argon 4s2 3d6. So the superscript here means number of electrons. And then, our number here 4, that's our energy level N, or our shell. And then S, that's our subshell. And then the superscript is the number of electrons in that subshell. So what's different here, it has the element argon in brackets. So essentially what this means, it's essentially like a save point. If you've ever played video games or something, it's a save point. So what this is saying is that this certain element has an inner core that looks like argon, and then we tack on these extra electrons to it. So it's like a save point, because remember how we said when we make these orbital diagrams, we always start at hydrogen and we work our way through until we get to the element we want. Well, if the element we want has like 79 electrons, like we would have to draw 79 different dots. But we can save some time by using a save point or a checkpoint where we can just start at a noble gas, like in this case argon, and pick up from there. So we would start at argon, we would go to the next period, which is n equals 4. So this is potassium and calcium are 4s elements. So both of those are filled since there's 2 electrons stated there as the superscript says. So potassium, calcium. And then there's 3D. So this first D block are the 3D elements. And it says that there are 6 electrons there, so we count over 6. Scantium, titanium, vanadium, chromium, magnesium, and then iron. Iron is our 6th element within that D block, so this element would be iron. Great. So this argon in brackets is just kind of like a checkpoint. It's saying that iron has the same inner core as an argon, and we just tack on these extra electrons to get to the iron element that we need. And you'll actually see, like if we look at some of these examples here, the inner shells of these orbital diagrams, they will always look the same. So all of them have, in their n equals 1, have 2 electrons in them. So all of them have essentially a helium structure. So we could use our save point, our checkpoint, to write out the electron configuration a little bit faster, like we have here. Okay, so the next example, what is the element that has 4 3p electrons? Okay, so we have to think, where is the 3p located on the periodic table? Well, I know that the p block is right over here, right, where it starts with boron, carbon, nitrogen, but it says 3. So 3 is our period number. So The p block starts with 2p at boron, and then aluminum starts off our 3p elements. So starting at aluminum, that's our 3p elements, but there are 4 electrons. So I'm going to count over 1, 2, 3, 4. So that brings us to sulfur. So my answer here would be sulfur. Has 4 3p electrons. Okay. And then finally, C has 2 electrons in the 4d sublevel. So kind of similar to the previous question, we have to locate where the 4d elements are. I know the D block is right here. It's the transition metals. The D block starts at 3d, and then the second row of the D block is 4d. So there's our 4d starting with yttrium, and it's 2 electrons in 4d. So I'm going to just count over 2. Yttrium only has 1 4d electron. So it's zirconium would have, 2 electrons in the, so it would be zirconium would have 2 electrons in the 4d sublevel. And so I'll just remind you with these different blocks that the S block always starts with 1s at hydrogen. The P block over here always starts with boron, and that always starts with 2p. There's no such thing as a 1p orbital because of our definition of how we get to subshells. And then finally, our D block that starts at scantium will always start at 3d. That first element within the D block is scantium. That is a 3d element. So it goes 1s is hydrogen, boron starts at 2p, scantium starts at 3d. So just keep that in mind. Okay. So, I said before, when we're learning about electrons, we're learning about reactivity of elements. And the reason the periodic table is arranged the way it is arranged is because we want to group together elements that have similar properties and similar reactivities with one another in the same column or the same group. The reason those elements react the same way or have similar properties and behaviors is because the elements in the same group have the same outer shell, outer shell electron configuration. And because the outermost electrons are the same, those outermost electrons, those are the electrons that are available to do reactions. They're the furthest away from the nucleus, so they're not held on to as tightly. Because remember, electrons are negatively charged and protons are positively charged. So those outermost electrons are the most free to do stuff in reactions, to take part in reactions. So this is why you see fluorine, chlorine, bromine, iodine, all those elements will react similarly because they all are in the same family, but more specifically is because all of them have the same type of outer shell electron configuration. So what do I mean by that? This outer shell configuration, these are the S and P electrons that are in the outermost ring of our orbital diagram. And we also call these valence shell electrons. These are the outer shell electrons. These are the ones that are going to take part in reactions. Thankfully, the two orbital diagrams we drew for phosphorus and nitrogen, you see both phosphorus and nitrogen are both in the 5A group. So they're in the same family. They should react. They should have similar reactivity, specifically because they have similar electron configurations or outermost valence electrons. So let's inspect the outermost shells of both of these elements. For phosphorus, the outermost shell is N equals 3. There are 2 3s electrons, and there's 1, 2, 3 p electrons, in this case 3p electrons. If we look at nitrogen, look, we have the same thing. We have 2s electrons, but this time it's 2s. We have 2s electrons, and we still have 3, in this case 2p electrons. So see how there's a total of 1, 2, 3, 4, 5 electrons in both of these outer shells. For nitrogen and phosphorus, they're in the same family. They will have similar reactivity. Because of the outer shell electrons, they have the same number. Those outer shell electrons are also called valence electrons. Valence electrons. And in both cases, for phosphorus and nitrogen, they have 5 in each of them because we count up valence electrons, we count up the outermost S and P electrons in the outermost shell of your orbital diagram. All right, so that explains a lot about, why the periodic table is built the way and arranged the way it is. I mean, I told you we, arrange things based on properties, but really it has to do with electrons, and that is what dictates similar properties in this case. So let's talk a little bit more about those outer shell electrons, valence shell electrons, so outermost electrons. So you're looking for the highest N value. So again, the highest shell or N energy level, I know I've been using all of those words interchangeably. In the highest shell, it's the sum of the P and S and P orbitals. Those are the valence electrons. So, if I ever ask you how many valence electrons are in sulfur, you count up all of the outermost S and P electrons, and that's how many valence shells there'll be. Thankfully, the periodic table tells you valence shell electrons. It's actually the group number for the representative elements, so all of these S and P block elements. So 1A through 8A, that number actually tells you how many valence electrons there are, but you can also just count outermost S and P orbitals. And then note for transition metals, so these are all, like the number B elements, so 3B through 12B. So 3B through 12B, they will all have 2 valence shell electrons. Because we're going to take, so that's just an exception that we're going to have. But for the most part, we're going to focus on the representative elements, the S and P block elements. All right. So like, for example, if I said oxygen, how many valence electrons are on an oxygen atom? Well, you could just look at the group number. It's group 6A. So there are 6 valence electrons in an oxygen atom. Or you could just count the outermost S and P electrons. So outermost would be this 2, N equals 2 period. So if you start at lithium, 1, 2, 3, 4, 5, 6. 6 elements to get to oxygen in the second energy level. So there are 6 valence electrons. And again, these valence electrons are the electrons that define reactivity, and they help us form bonds once we get into Lewis structures, and creating different molecular compounds. So the number of valence shell electrons also tell us chemical properties of that elements, and it's what establishes the periodic law that all of the elements within one group will have the same number of valence electrons. I'll just write that: elements in same group have the same number of valence electrons. Okay. Are we going to do some practice? No. Okay. I'll just, I guess, prove to you that, the group number and valence shell electrons are the same. All right. So in this example, elements in group 2A all have 2 electrons in their outermost s orbital. So that's why they're named group 2A, and they all have 2 valence electrons. So if I kind of do my shortcut thing before that I've been showing before, my checkpoint, if I wanted to write the electron configuration for beryllium, a shortcut way would be to start at helium and write 2 s electrons. That's what I have here. So you see that there are 2 electrons in its valence shell, 2 electrons in that s orbital. So there are 2 valence electrons in that s orbital. So next up is magnesium. I could write a shortcut way. So start with a neon core that gives us 10 electrons, and then 3 s2, because magnesium is the second element into our third period. Next is calcium. So my shortcut is argon. I'm going to start at argon to potassium, then calcium. So that's 2 elements into the 4s. And then finally strontium. My shortcut is krypton and 5s2. So you see in all of these elements, I mean, I could have drawn the full-blown like orbital diagram, but I don't think that's necessary. You see in all of them that there are 2 valence electrons in all of those elements. So you will see similar, I'm not going to say same, similar properties and reactivities. So let's make sure we can figure out the number of valence electrons for these different elements. So this first one is phosphorus. So remember, valence electrons, outermost s and p electrons. So for phosphorus, you could also look at the group number. So phosphorus is in group 5a, but you can also count all of the elements in that row. So the third period starts at sodium. So sodium, 1, 2, 3, 4, 5. 5 elements to get to phosphorus. So there's going to be 5 valence electrons. And I already showed this in that previous example. Okay, so germanium, let's find germanium. Okay, germanium's right here. It's a metalloid. It's in group 4a. So you would predict it would have 4 valence electrons, but let's just check this out. So we're in period 4. We're going to start at potassium, the S block, so potassium, calcium, 1, 2, gallium, 3, germanium, 4. So that's 4 valence electrons. And then finally, fluorine. It's in period 2, group 7a, so you'd predict it would have 7 valence electrons, but we can still count. Start at lithium to beryllium, 1, 2, boron, 3, carbon, 4, nitrogen, 5, oxygen, 6, fluorine, 7 valence electrons. All right, so it's as simple as that. The periodic table tells you, or you can count the elements in that row to get to that element. But only count s and p electrons to count towards your valence electron count. Okay, so we're going to talk about one last way to represent valence electrons. Because writing out full-blown orbital electron orbital diagrams isn't very fun. Like I said, all of the reactivity and the reactions, properties that you're going to see are because of the outermost electrons. So why don't we just ignore the innermost electrons? Like here in phosphorus, like if I wanted to think about bonding in phosphorus, all that bonding is only ever going to occur in this outer shell. Can we just kind of ignore the inner shell? And we really can, because noble gases, all of these different shells are essentially noble gas configurations. That's what gives us our shortcuts. We can ignore those because noble gases are super stable and do not react very often. So how we represent valence electrons for our bonding pictures, once we get to chemical bonding, is with Lewis dot structures. This is our way to represent our outermost electrons. Outermost. So how we do this to simplify our electron picture is to denote how many valence electrons are around an element. The first thing you need to do is write out the chemical symbol, the 1 or 2 letter chemical symbol, and then you will only draw out the valence electrons using this form. You'll put the s electrons on the east side of the element name, and on the northwest and south sides you will put your p electrons. And I already kind of showed that using the orbital diagrams previously. So it'll look like this, where we have each dot represents an electron. So on this right side we have our s electrons, and then on the other sides we can have our possible p electrons. So this isn't really any different than orbital diagrams. It's just simpler because we're only drawing the valence electrons. Okay, so let's do some practice. So let's do hydrogen. All right, hydrogen has 1 electron. Well, let's do valence electrons first. Okay, so hydrogen will have 1 valence electron. Helium has 2 valence electrons. Sodium has 1 valence electron because it's in group. Again, I'm just doing the group numbers. Helium is one of our exceptions. Remember, helium only has 2 electrons in it. If we actually wrote out the whole electron orbital diagram, it only has 2 electrons in its n equals 1 shell. So there's only one ring, so there's only two valence electrons, because those are the only electrons there. All right, but then sodium, because its inner shell is a neon core, its outermost electron is a 3s electron, so that's sodium. There's only one valence electron. Calcium, it's in group 2a, so that's 2 valence electrons. And then oxygen is in group 6a, so there's 6 valence electrons. And then finally fluorine, 7a, it has 7 valence electrons. So let's take a stab at writing out Lewis dot structures. First step is to write out the chemical symbol, which I have here. So I'm going to draw hydrogen. There's one valence electron in hydrogen. Take a look. It's within the s block. So that valence electron is an s electron. So you're going to put it on the east side over here. So that's how you would draw hydrogen. You would not draw it like this. Typically not. If we were just talking about one hydrogen atom. All right, so then helium. Helium looks like that. There's 2 valence electrons. They're both s electrons. So you need to pair them together to denote that they're in the same orbital. So you will draw helium like this, with 2 electrons paired together. This would not be correct, because this, having the electrons opposite of one another, you are indicating that these electrons are not in the same orbital, but they are. These are both 1s electrons. One is spinning up and the other is spinning down. Okay, sodium. There's only one electron. It's an s electron in its valence shell. So I'm going to just stick it right there on the east side. Calcium. Okay, 2 electrons. They're both s electrons. So 1, 2. Again, they're paired because they're both s electrons. You're not going to write it like this. That indicates that they're not paired. That would not be correct. All right. Oxygen, there are 6 electrons, where 2 of them are s electrons and 4 of them are p electrons. How did I know that? Oh, I just looked at the periodic table. All the information is there. You just need to know how to use it. So oxygen's right here in period 2. So let's start at the beginning of period 2. Lithium, beryllium. Those are 2 s electrons. Boron, carbon, nitrogen, oxygen. Those, you have to move over 4 elements in the p block to get to oxygen. So that's 4 electrons to get to oxygen. So that's where those 4 p electrons come from. Okay, so this is where things kind of change. So I have oxygen. So let's fill all those electrons. Those s electrons fill first on the east side. Now I have to fill the p electrons, but we still have to keep our same rules about spreading out electrons within a subshell. So we need to spread out those p electrons. So I need to put 4 of them around the oxygen. So I will do this. 1, 2, 3. They're all spread out, but there's nowhere else I can put them without doubling up, which is fine. Now we can start pairing for that 4th electron, and I'll just put it right there. So you see that there are 6 electrons total around oxygen, where 2 of them are paired in the s orbital, and then the other 4 are in p orbitals, all right? And you spread them out before you start doubling up. A good question might be, how many unpaired electrons are in an oxygen atom? And so unless, if you did not pair things up correctly and you didn't spread things out, you might not get this question right. All right, so as I've drawn here, the correct way to make a Lewis structure for oxygen, there are 2 unpaired electrons, all right, in the p orbital. And then one of the p orbitals is completely paired, and so is the s orbital. All right, finally, fluorine. So again, look at fluorine. It's just 1 over from oxygen. So it's also going to have 2 s electrons and some p electrons. This time it's going to have 5. So I'm going to start this out the same way. Start with the element symbol. Fill up those s electrons first. So I got the 2 down. And now I need to put 5 p electrons. So I'm going to put 1, 2, 3. Spread them all out. Now I can start doubling. 3, 4, and 5. So you can see that fluorine has 1 unpaired electron based on its Lewis structure, Lewis dot structure, sorry. Okay, come on, let's finish this out. So you can see from these Lewis dot structures that we made that there's only room for 8 electrons, right? I talked about like east, north, west, south directions of the element. There's only space for 8 electrons total because there's only 4 sides. All right, that number 8 is significant because what elements have 8 electrons? It's the elements in group 8A, which you can see are our noble gases, neon, argon, krypton. All right, so 8 is a significant number because 8 is the most stable electron configuration, which is the noble gas. And what I mean is outermost or valence electrons or outermost. So when those outermost electrons, when your valence electrons, when you draw your Lewis dot structure, when all orbitals are filled with 8 electrons, you essentially have a stable element. That element, there's no need to start to gain or lose electrons. It's stable, meaning that no reactions occur or will occur. No reactions will occur. So, we look back at some of these examples. Atomic oxygen and atomic fluorine, these are very, very quite reactive because there's this spot missing. Fluorine has this electron spot missing. It wants to fill that electron. I don't like to say wants. It is very energetically favorable for fluorine to fill up that empty electron spot. This oxygen has 2 unpaired electrons. I don't want to say that atomic oxygen wants to fill up these unpaired electrons, but it's very energetically favorable for oxygen to gain electrons, so it has a valence shell count of 8. So atomic oxygen and fluorine are very reactive because of these unpaired electrons. And because of the absence of unpaired electrons, that makes all of the noble gases very stable with 8 electrons. And then our exception, remember, is helium. Helium is also a noble gas, but because it's a 1s element, it only needs 2 electrons to completely fill its shell and not be reactive anymore. Helium is also very stable. That's why it is a noble gas. Okay, so yeah, example, let's draw the argon Lewis dot structure. All right, to kind of drive this home, argon group 8A, but you can see, argon is in period 3. So if we start at sodium to magnesium, that's 2 s electrons that I'll place right there. Now I'm in the p block starting at aluminum, going to argon. Those are 6 p electrons. So I'm going to go 1, 2, 3, 4, 5, 6. So you see that all around argon has 8 electrons. That electron configuration is very stable because it has 8 valence electrons. There are 8 outermost electrons. I don't know how else to say it. This is very stable. There are no unpaired electrons that will cause reactivity. Okay. All right. I think now it's basically it now. I just kind of want to summarize things that, these Lewis dot structures and valence electrons, this is what defines reactivity for us. All atoms are trying to achieve noble gas configurations. Okay? Through different reactions, through forming bonds, atoms need, or it is energetically favorable for atoms to achieve a noble gas configuration and have 8 valence electrons, or sometimes 2 for hydrogen, which we'll talk about in a later chapter. So where if there's 8 valence electrons, 2 of those electrons come from an s orbital and 6 come from a p orbital. And then again, because elements in the same family have the same number of valence electrons, they have similar reactivity because atoms react to achieve noble gas configurations. And then again, this explains why noble gases are not reactive at all. The only noble gas that does participate in reactions is xenon. So if you see xenon is all the way down here, it's in period 1, 2, 3, 4, 5. So it's an n equals 5. Neon is a really big atom. And because those electrons are so far away from the xenon nucleus, it can actually react with other elements, essentially only fluorine because it's very reactive. So that's our one exception. Xenon can have reactions, but we're not going to really talk about xenon too often. Just know that noble gases are very unreactive because of, no, not because of noble gas. It's because it has 8 valence electrons. That's why we call them noble gases, because there's already 8 valence electrons. They are already stable elements. There's no need for reactions to occur. Noble gases do not get any energy out of undergoing chemical reactions. Okay, so again, periodic table tells us tons of stuff. Periodic table tells us everything about chemistry. It tells us number of protons, electrons. It gives us an idea about neutrons based upon their molar masses or atomic weights, although they're weighted averages, but it still gives us an idea about neutrons. The periodic table tells us whether things are metals or nonmetals or metalloids. We have different names of families or groups of elements, those representative elements like the alkali metals, the alkaline earth metals, the halogens, the noble gases, things like that. It tells us about the different subshells, the different orbital blocks, S, P, D, and F, that they're all right here. That's why the shape of the periodic table is the way it is. We have the D's, we have the S's, and we have the P's. It tells us order of electron filling, so we don't have to memorize it. It can tell us the number of valence electrons, and it also gives us an idea about reactivity. You know, we related reactivity to number of valence electrons. So let's see if there's a trend there. I think this is the last thing that I want to talk about, is that, you know, the further you're away from a noble gas configuration, the more reactive that element is. So here are the trends based upon reactivity, which is based upon number of valence electrons. So reactivity, essentially, because valence electrons are very far away from the nucleus, they're the furthest away, that those valence electrons are the ones participating in reactions. So when you go down a group, the further you get away from the nucleus and that positive charge, the more reactive the element. All right, you can think of like an atom as a mom or a parent wrangling up their kids. Okay, and so, you know, the parent is the nucleus, and the different shell or sub energy levels are the reach of that parent. And so if that parent has a kid running around, the further away from the parent that kid is going to be more reactive because it is further away from its parent that can discipline it or, you know, tell it don't do the thing you're doing, right? So the further an electron is from the nucleus, the more reactive that element is. So as you go down a group, so let's not look at the halogens. Let's look at group 1A. We go down from lithium all the way down to cesium, the 1A elements, the alkali metals. Lithium will be the least reactive, while cesium will be the most reactive within this group, because cesium has its valence electron furthest away from the nucleus. That kid is the furthest away from its parent, and it's going to run amok. Okay, so then another trend is across a period, so going from, like, you know, lithium, beryllium, all the way to fluorine, as you go across a period, you're increasing your atomic number. So you have more protons in your nucleus, right? So if there's more protons in that nucleus, the electrons are being held tighter. All right, so the parent is holding all of its children closer to itself. So protons, I guess, could be like, you know, mom or the parent's strength in wrangling their kids. And so the more protons, the more strength that parent has to wrangle their kids, the less reactive that atom or that element is going to be, the element. Okay, so that means if we put those things together, down a group, more reactive, across a period, less reactive, that would make cesium the most reactive element in its elemental form, and it would make helium the least reactive element in its elemental in its atomic form. Okay, so that kind of summarizes atomic structure. I know this was a doozy, it was a long one, but it's really important that we kind of lay this foundation of reactivity where it comes from. It comes from electrons. We've talked a lot about protons and neutrons and masses of atoms in the past couple lectures. Now we're talking about electrons, and we're actually going to get into the chemistry of elements and think about how do things combine with one another. So that is it for chapter 7. Again, right here is where we're going to end the content for midterm 1.